Hello friends, I welcome you to my lecture on the method of successive approximation. Let us consider a Volterra integral equation of the second kind by x equal to fx plus lambda times integral a to x kxt by t dt, and let us assume the conditions that fx is continuous on the closed interval a to b and the kernel kxt is continuous for a less than or equal to x less than or equal to b and a less than or equal to t less than or equal to x in that region. Now what we will do here is that we shall start with some by naught x initial approximation to the solution by x of the given differential equation. So we shall start with some by naught x as the initial approximation, which we will take as continuous function in AB and put it into the right hand side of the equation 1 in place of by t. In place of by x, when we put this, then we will get by 1 x equal to fx. The first approximation to the solution by x we get as by 1 x equal to fx plus lambda times a to x kxt into by naught t dt. Now after we have found by 1 x here, we then put by 1 x in again in the equation 1 to get the next approximation, that is by 2 x. So since by 1 x is continuous in the closed interval a b, we can put by 1 x in place of by x in the right hand side of equation 1 and obtain the second approximation by 2 x to the solution by x of the given integral equation. So by 2 x is fx plus lambda times integral a to x kxt into by 1 t dt. Now we can continue this process, and then continuing this process we shall obtain a sequence of functions by naught x, by 1 x, by 2 x, by n x and so on, where the expression for by n x will be given by n x equal to fx plus lambda times integral a to x kxt into by n minus t dt. Since we have assumed kxt to be continuous, fx to be continuous and kxt to be continuous in the region a less than or equal to x less than or equal to b and a less than or equal to t less than or equal to x, it turns out that the sequence by nx converges as n goes to infinity to the solution by x of the integral equation, given integral equation. Now a suitable choice of the initial approximation, which we call as zero approximation by naught x, can lead to a rapid convergence of the sequence. So if we suitably choose the zero approximation by naught x, we can reach the solution of the integral equation faster. So that is very essential, how to choose the zero approximation by naught x. Now let me show you how we apply this method to a given integral equation. By x is equal to, let us consider by x equal to 1 plus integral 0 to x by t dt, and let us assume by naught x to be the equal to 0, that is we are assuming 0 solution to the given integral equation. So what we will do to obtain the first approximation by 1 x, let us put by naught x equal to 0 in the right hand side of the given integral equation. So here we put by naught t, so by 1 x will be 1 plus integral 0 to x by 1 t dt, and by 1 t by naught t dt, by naught t dt is equal to 0. So we will get by 1 x equal to 1, and then we put by 1 x in the right hand side of the given integral equation to obtain by 2 x. By 2 x is then 1 plus integral 0 to x 1 dt. So this is 1 plus x. Then by 2 x is put in the right hand side of the given differential equation to obtain by 3 x, and by 3 x is 1 plus x square by 2, which is again put on the right hand side of the given integral equation to obtain by 4 x. By 4 x is then 1 plus x, we can write x square by 2 as x square by 2 factorial, and then we also have the x cube by 3 factorial. So this way when we carry on, so similarly by nx is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on, x to the power n minus 1 over n minus 1 factorial. Thus we notice that by nx is the nth partial sum of the Maclaurin series for e to the power x. The Maclaurin series for e to the power x is given by sigma n equal to 0 to infinity x to the power n by n factorial, and hence as n goes to infinity by nx, the nth partial sum converges to the sum of the series, that is e to the power x, and so we can say that by x is equal to e to the power x, and we can also verify that by x is equal to e to the power x is a solution of the given integral equation. You can see that. So here you put by x, let us see, we have by x equal to 1 plus integral 0 to x by t dt. Let us verify that by x is equal to e to power x is a solution of this. So let us take the right hand side. This is 1 plus integral 0 to x. Let us put by t as e to the power t here. So we get 1 plus e to the power t 0 to x, which is 1 plus e to the power x minus 1. So what we get is e to the power x. So left hand side, in the left hand side by x is e to the power x. So the left hand side and right hand side are both equal. Okay, LHS is equal to by x equal to e to the power x. So thus LHS is equal to RHS when by x is equal to e to the power x. So e to the power x is a solution of the integral equation by x plus by x equal to 1 plus integral 0 to x by t dt. Now let us take one more example. Say we have y x equal to 1 plus integral 0 to x x minus t y t dt, where we are given the 0 approximation by naught x as equal to 1. So for all values of x over the range of values of x, we are assuming by naught to be equal to 1. So here by 1 x, the first approximation by 1 x is given by 1 plus integral 0 to x by naught t dt, and by naught t will be equal to x minus t into by naught t dt. By naught t is equal to 1. So we get, after integration we get 1 plus x square by 2, and then we put by 1 x in the given differential integral equation. For by t we put by 1 t in the right side to get by 2x. By 2x is 1 plus integral 0 to x x minus t into 1 plus t square by 2 dt. So after integration and simplification we get 1 plus x square by 2 factorial plus x4 by 4 factorial. We can again continue this, and we can find by 3x by putting by 2t in place of by t here. So by 3x will come out to be 1 plus x square by 2 factorial plus x4 by 4 factorial plus x6 by 6 factorial, and generalizing we get by nx as 1 plus x square by 2 factorial, x4 by 4 factorial plus x6 by 6 factorial, and so on, x to the power 2n by 2n factorial. So as n goes to infinity, by nx goes to by x, which is sigma n equal to 0 to infinity x to the power 2n by 2n factorial, and it is known that this is nothing but e to the power x plus e to the power minus x by 2, and we know that e to the power x plus e to the power minus x by 2 is the cos hyperbolic x. So the solution of the integral equation, given integral equation, is by x equal to cos hyperbolic x. So this is how we apply this method. Now let us consider Volterra integral equation of the first kind. We shall see that Volterra integral equation of the first kind can be converted into a Volterra integral equation of the second kind, and we can obtain the solution there, and that solution will also satisfy Volterra integral equation of the first kind. So Volterra integral of the equation of the first kind can be written as integral a to x kxt by t dt equal to fx, where by x is the unknown function. Let us assume that the kernel kxt and its partial derivative with respect to x are continuous in the range are in the region a less than or equal to x less than or equal to b, and a less than or equal to t less than or equal to x. Then from the given first order Volterra integral equation of the first kind, it is clear that when x is equal to a, fa must be 0. So it is clear from the given equation that the condition fa is equal to 0 is necessary for the equation to possess a continuous solution. Now differentiating both sides of this equation 2, what we get is, using the Lebanese rule for differentiation under sign of integration, we will get integral a to x derivative of kxt with respect to x into yt dt. Then we put t in place of t, we put x, the upper limit. So we get kxx into yx and then d over dx of x, and then minus in the integrand we put t equal to a, the lower limit. So we get kxa into ya and then derivative of a with respect to x, and right hand side will become f prime x. Now since a is a constant, dA by dx will be 0. So we will, this equation will reduce to integral a to x kx dash xt into yt dt plus kxx into yx equal to f dash x, because derivative of x with respect to x is 1. So now so let us assume that kxx does not vanish at any point in the interval a b. Then from equation 3, by on dividing by kxx both the sides, we will have by x equal to f dash x over kxx minus integral a to x kx dash xt over kxx into yt dt, where you can remember that kx dash xt is the partial derivative of kxt with respect to x, and it is a since kxt function is known, fx function is known, so f dash x over kxx is known, and kx dash xt over kxx is also known. So it is a Volterra integral equation of the second kind, where we can take lambda to be minus 1. Now if it happens that kxx is 0 in the interval a b, then this equation will reduce to integral a to x kx dash xt into yt dt equal to f dash x. So if kx x is equal to 0 for all values of x in the interval a b, then we again get the Volterra integral equation of the first kind. So what we will do is, now let us assume that second derivative of kxt with respect to x is continuous in the domain a less than or equal to x less than or equal to b, a less than or equal to t less than or equal to x. Then we differentiated again with respect to x by using Lebanese rule. So we shall have integral a to x kx second order partial derivative of kxt with respect to x into yt dt plus kx dash xx into byx dx by dx minus kx dash xa by a into dA by dx equal to f double dash x. Now a is a constant, so dA by dx will be 0, and therefore this equation will reduce to integral a to x kx double dash xt by t dt plus kx dash xx by x equal to f double dash x. Now as before, if the first order partial derivative of kxt with respect to x at t equal to x is non-zero for any x in the closed interval a b, then we can divide this equation by kx dash xx and arrive at Volterra integral equation of the second kind, by x equal to f double dash x over kx dash xx minus integral a to x kx double dash xt over k dash xx kx dash xx into by t dt, and we can solve it by the methods of solving Volterra integral equation of the second kind. Now if again kx dash xx is identically 0, then we shall use the same procedure. So if it so happens that we have to continue this procedure, and the pth derivative of kxt is continuous, the pth derivative of kxt with respect to x is continuous in the domain a less than or equal to x less than or equal to b, a less than or equal to t less than or equal to x, then fpx is also continuous, and so we shall have integral a to x kpxt by t dt plus kxp minus 1 xx by x equal to fpx. Now when kxp minus 1 xx is not 0 for any x in the closed interval a b, we shall be dividing this equation by kxp minus 1 xx and arrive at Volterra integral equation of the second kind. So this equation has a unique solution, the question 5, and the solution so obtained satisfies all the intermediate equations which we have got, as well as the given integral equation, that is equation number 2. Now this is how we apply use this method. So let us see how we can solve Volterra integral equation of the first kind. Suppose we have this Volterra integral equation of the first kind. So we have by integral 0 to x e to the power x minus t into by t dt equal to sin x. We can see here that fx is equal to sin x and kxt is equal to e to the power x minus t. So fx is a continuous function and kxt is also a continuous function. Now let us differentiate this equation with respect to x by using Lebanese rule. So let us recall the Lebanese rule, the d over dx of integral gx to hx fxt dt. Let us say capital fxt, where we can take this is integral gx to hx partial derivative plus f x x and then instead of x we have hx. Minus f so this is the formula. So let us apply here. So when we differentiate with respect to x, we have which is cos x. Okay. Now let us apply the Lebanese rule. So this is integral 0 to x we put the upper limit we get this. So this gives you 0 to x, partial derivative with respect to x gives e to the power x minus t by t dt, and here we get by x equal to cos x, and which can be written as so you can see that the coefficient of by x is 1, which is not 0. Okay, so we can write it as by x equal to cos x minus integral 0 to x e to the power x minus t into by t dt, which is a Volterra integral equation of the second kind. Now we shall solve it by the method of finding the resolvent kernel. So here we notice that here fx is equal to cos x, lambda is equal to minus 1, and kxt is equal to e to the power x minus t. So let us find the iterated kernels first. So we have k1xt is equal to kxt is equal to e to the power x minus t, then k2xt is equal to integral t to x kxz into k1 zt dz. Okay, so this is equal to integral t to x kxz is e to the power x minus z, and then k1 zt is same as kzt, but kzt will be equal to e to the power z minus t dz. E to the power x minus z into e to the power z minus t is e to the power x minus t. So, integral t to x okay. Now, e to the power x minus t is independent of z, so I can write it outside, and then we integrate and find the value of k2xt as e to the power x minus t into x minus t. Now, let us find k3xt. So, k3xt is integral t to x kxz k2 zt dz, which is equal to k2 zt will be equal to e to the power z minus t into z minus t, and this is now e to the power x minus t integral t to x and z minus t dz. When you integrate this and substitute the limits, what you get is e to the power x minus t into x minus t whole square by 2. Now, if we find k3xt, k3xt will come out to be, so similarly it will come out to be e to the power x minus t into x minus t whole to the power 3 divided by 6, which can be interpreted as e to the power x minus t into it is k4 not k3, k3 we have already found. So, this is e to the power x minus t raised to the power 3 divided by 3 factorial, and this 2 we can interpret as 2 factorial. So, generalizing we have knxt equal to e to the power x minus t raised to the power n minus 1 over n minus 1 factorial. Okay, now let us find rxt lambda. So, now rxt lambda is summation n equal to 0 to infinity lambda to the power n k n plus 1 xt. So, let us put the value of lambda n k n plus 1 xt here and determine the sum of the series. So, summation lambda is equal to minus 1. So, we have minus 1 to the power n, and k n plus 1 xt is e to the power x minus t into x minus t to the power n divided by n factorial. I can write it as e to the power x minus t times summation n equal to 0 to infinity minus 1 to the power n. I can multiply to x minus t to the power n and write t minus x to the power n divided by n factorial. Now we know the sum of this series, sigma n equal to 0 to infinity t minus x to the power n by n factorial. This is e to the power t minus x. So e to the power x minus t into e to the power t minus x. So we get e to the power 0, which is equal to 1. So we have found the value of the resultant kernel rxt lambda, which is equal to 1 here. Now we can proceed to find the solution of the Volterra integral equation of this second kind. So we have by x equal to cos x minus integral 0 to x e to the power rxt lambda is 1 into ft, that is cos t dt. So we have cos x minus sin t 0 to x, and which will give us cos x minus sin x. So by x is equal to cos x minus sin x is the solution of the Volterra integral equation of the second kind, by x equal to cos x minus integral 0 to x e to the power x minus t by t dt, and from the method it follows that it is also the solution of the given integral equation of Volterra integral equation of first kind. So the solution of this Volterra integral equation of first kind is by x equal to cos x minus sin x. That is all I want to say. Thank you very much for your attention.